Welcome everyone. I'm Dr. Sylvain Barde. I'm a lecturer at the School of Economics here at the University of Kent, and I would like to talk to you today about research I've been doing about the problem of navigating the wilderness of economic models. Before I actually start talking about what my research actually is, I need to maybe better explain or better define what the problem actually is. And it centers around the following set of questions. Why do we use models in economics or even in science to understand the world? What are they? And how do we determine if the models are any good? Okay, if they're actually useful in bringing us understanding? My work involves that third question. But before that, I need to present the first two questions. And the first two questions, actually, the answer is relatively simple, and it's nearly always the same for every field of science. Reality in itself is incredibly complex. Okay? Imagine if you tried to understand everything that's going on in this picture. Every dot of light is an individual that's making a decision whether to turn left, turn right, think about what they're going to have for dinner or what they're going to do tomorrow. The amount of data you'd need to keep in mind to directly apprehend what's going on is just not possible. And this is just one city, one night. Okay? So of course, what that means is we have to simplify. And that's what a model is. A model is simply a simplified representation of reality that allows us to understand what is actually going on. Within economics, this involves a trade-off usually when we design models, okay, between simplicity and complexity. We typically make a lot of assumptions to simplify models. So this is an example of some, it's not all of them, but the most important one that we usually make is we make the assumption that our agents, our firms, our households, are fully rational. So that means that given a set of alternatives, the agents will always try to find and pick the one that makes them as well off as they possibly can. Okay? So they will do all the calculations and always pick the optimal solution. In reality, people probably don't behave that way. They probably adopt a behavior where, they've got bounded rationality. They are rational. They do want to make themselves better off, but once they reach a particular threshold, for example, where they're happy enough, they stop searching. They're not going to seek out the absolute maximum welfare. Another one that we typically make is that agents don't interact amongst each other, which sounds paradoxical because economics is all about agents buying and selling off each other. Okay? But the idea is actually that you only interact with the market. If I decide to buy a new smartphone, the only pieces of information that are important in that decision are my preferences over smartphones and perhaps who sells them and at what price. And that's the only information I need. In reality, what we know is that a lot of our beliefs and our preferences are influenced by other people. If I'm a teenager trying to buy a smartphone, then what my friends in my social circle believe about brands of smartphones is going to matter a lot in my decision, not just the price and where I can buy it. And so we have a situation where my beliefs depend on other people's beliefs, and as you can see, everything becomes very, very complex. So we make these simplifications for a good reason. We understand the world is more complex than our assumptions would suggest. Why do we do this? We do this because it buys us tractability. It buys us the ability to solve the models, to actually get an equation that describes the solution. In many cases, the solution is unique. And also, it allows us to estimate these equations using statistical techniques, get parameters for these equations, and then allow us to use the models to make predictions and help policymakers make decisions. That's what the assumptions buy us. On the other side, the models where these assumptions are relaxed tend to be you can only simulate them. You can't actually write down an equation which uniquely describes the solution. Okay? And on top of that, there's a wilderness of models. Okay? This is the Anna Karenina principle from Tolstoy. All happy families are alike, and all unhappy families are unhappy in their own way. And it's the same thing with economic models. Nearly all optimal rational models are the same, but all boundedly rational models are boundedly rational in their own way. there's many, many ways in which agents can be not quite rational, and that leads to a wilderness of models, a multiplication of models. And this is a term that was coined by Professor Klaus Homs, who's one of the real pioneers in this field and drivers of this field, and it generates this problem where there are many, many, many models that we have to try and discriminate amongst them. Okay? So typically, historically, economics has lived on the left-hand side of this divide, where basically we have made these simplifying assumptions and got models that are simple to work with. This led to a problem around the time of the financial crisis, and Olivier Blanchard, who's the head researcher at the IMF, basically made this statement, which is very illuminating, about the fact that those models that we traditionally use are absolutely fine in normal times when the economy worked in a well-behaved manner. But sometimes the economy malfunctions and enters a dark corner where we don't know as much because it all depends on these more complex models that we don't understand. So we do need a better understanding of these complex models so that they allow us to explore the darker corners of the economy when things go wrong. The problem? Well, the problem is that at that point we're relying on models that are difficult to work with and also on a wilderness of models where there are many, many models, many ways of modeling, and we have very few tools to allow us to identify which one's better than which. And this is where my research comes in. So let me start by giving you an example. What I've done here is I've plotted 4 pieces of data. Each one of them is the daily percentage change of a stock market index. It's what you get when you listen to the news in the evening and you hear that today the FTSE 100 closed on a 2.5% increase. Okay? And you have that for every day. 3 of these are simulations. One of these is the real thing. It's the New York Stock Exchange. Which is which? Immediately, hopefully, you can see that one of these is not like the others. The one on the bottom right is not quite the same. The patterns are not right. So either that's the real data and the other 3 are simulations, and they're pretty bad simulations because they don't replicate the real thing, or more likely, it's a simulation and it's a pretty bad simulation because it doesn't match the other 3, one of which is the real data. Okay, and that's actually the case. The answer here is that the one on the top right is the Dow Jones Index, okay? And that's the real data. The other 2, ALW and FW, are simulations that approach the data better than the 3rd simulation, GW. The letters here refer to the initials of the authors who designed the models. The important thing is all 3 models all contain the same basic mechanism, which is that investors in these markets can switch opinions. Okay, they are divided in between people who believe that the market's going to continue on its route, whether it's going up or going down, and people who believe that actually it's going to change directions. And those beliefs are contagious. So an optimistic person might bump into a pessimistic person and all of a sudden become pessimistic himself. Okay? And you can imagine that through that mechanism you might have contagion of panics. Okay? And that's what's happening here. So already your eyeballs are telling you that the 2 models on the left are better than the model on the bottom right. But which of those 2 models is closest to the real thing? And this is where you need to have better tools. Okay? And this is where my research comes in. I have developed a methodology, a tool for measurement, which I call the Markov information criterion, which relies on essentially 2 tricks to actually get a measurement. The first is that a lot of these economic models, okay, that are all very different and that all live on that spectrum that I talked about earlier, are actually deep down all part of the same family. Okay? They are all parts, or they can all be represented as a Markov process, which is a mathematical representation of these models. So what you can do is you can represent all these models as a Markov process and then compare them because you're comparing models in their same state. The second trick is to realize that this problem of comparing the 2 models or calculating the distance between a model and some data is actually exactly the same problem as data compression. In terms of information theory, it is exactly the same problem. Okay? So what my research does is to modify an existing data compression algorithm into a measurement tool. Okay? And I use the specific tool that I use because it is proven to provide the best possible measurement for all Markov processes. And because my economic models can be reduced to Markov processes, it means that I can provide optimal measurements on all these economic models. So to show you that actually this works, here's an exercise I did where what I did is I compared pairs of models, one of them better than the other. Okay? And so obviously I get a distance between the worst model and the better model. And sometimes the models are very close, so the distance is very, very small, and sometimes the distance is bigger. On the horizontal axis, I'm using a traditional measurement because I'm using a model that I can use a traditional tool on, and I'm using the log likelihood as, or the difference in log likelihood as the measurement of how far apart from each other these models are. Okay? On the vertical axis, I'm showing you my own tool. And what that shows is that everything lines up. My own tool agrees with the measurements you get from the traditional method. Okay? It's not perfect. There's a bit of a cloud, so there's a bit of noise included in that measurement. But if you look at the row, which tells you the correlation between the two measurements, the correlation is 0.97, which is incredibly high. And what that means is that my tool is a highly reliable measurement of distance between models. The only difference is that my tool can be applied to models where traditional tools fail. What happens when you apply this measurement tool to the three models that I've showed you earlier? Well, what you get is this. And this is a plot of the performance of these three models over time relative to a benchmark model, the T-Garch model, which is just a standard way of representing financial data. What you can see, first of all, the dark grey line at the top, that's the simulation model that was at the bottom right, the one that wasn't very good. And what you can see is the distance is much higher than the other models. Okay? So what that tells you is, indeed, it does perform worse than all the others. The other two models, the light grey and the white lines, these ones are much closer to zero. The distance is much smaller. And not only that, they're very similar to each other because the two lines move in the same way. But, nevertheless, you can tell that the model in white, which is FW, beats the other model on average because the line is below. More importantly, it is very often the case for those two models that they go below zero. In other words, the distance is negative. What that means is they beat the traditional model. They beat the T-Garch. They are closer to the data. Okay? So those simulation models can actually provide a better description of the reality we see than more traditional models. And finally, this is especially true for 2008, where you see this big spike, where all the models improve in performance dramatically during that financial crisis. Even the worst performing model all of a sudden sees a massive boost in performance. Okay? What does that tell us? That tells us that the core mechanism, this panic, this contagion of opinion in the market, is actually potentially a very important explanatory factor for what went wrong in those financial markets at that point. Okay? What this tool provides is, in some sense, a flashlight to explore the dark corners, to actually allow us to measure these models against each other, and as I said earlier, navigate the wilderness by identifying which model beats which model is more useful in which circumstance. Okay? This is just the start. The future plans, first of all, is in collaboration with a team of researchers who are all working on similar questions, because this is not a field in which I'm working alone. There's a lot of people working on similar things. We are aiming to develop a common standardized toolbox containing all the various tools that we've developed, which we can make available to the research community and allow them to improve their simulation models. And finally, our hope is also to work with some of the central banks. This is something that is starting to get into process because they are very keen to develop their own simulation models so that they can also start understanding or simulating situations where the economy goes wrong and learning what to do in those simulations. And they need the help of these tools that we want to provide in order to do that and improve their models, improve their predictions, and themselves understand how to navigate that wilderness. Thank you for your attention.